It's a beautiful day in this neighborhood, a beautiful day for a neighbor. Would you be mine? Could you be mine? It's a neighborly day in this beauty wood, a neighborly day for a beauty. Would you be mine? Could you be mine? I have always wanted to have a neighbor just like you. I've always wanted to live in a neighborhood with you. So let's make the most of this beautiful day. Since we're together, might as well say, would you be mine? Could you be mine? Won't you be my neighbor? Won't you please? Won't you please? Please won't you be my neighbor?
Good afternoon, everybody. Welcome to Tibbetts Physics. What is crappinin'? Today, we're going to talk about refraction, or more specifically, how light interacts with other mediums or materials. To begin with, we're going to start with an analogy of driving a car from one medium to the next, or one material to the next. So let's draw a barrier, and we'll say that you're going from pavement into mud. And just like the law of reflection, for refraction we have to draw the normal, which is a perpendicular line to the surface. So why don't we draw a top-down view of a car. Here we've got our rear wheels, here's our front wheels, and it's going towards the mud. As we could see, the front right wheel is going to hit the mud first, and the left front wheel is still going to be in the pavement. Because the right front wheel is going into the mud first, it's going to slow down as it's going into more dense material, and the wheel that's still in the pavement is going to go faster, even though it's at the same speed, but it's going faster relative to the wheel in the mud. So because it's going faster, that's going to cause the car to turn inwards, and it's going to bend towards the normal once the entire car goes in the mud. So if we draw our after picture, I'm just going to draw this line to show that it's hitting the normal. If we draw our after picture, the car is going to bend inwards towards the normal. We'll draw our wheels. Sorry that it kind of shrunk a little bit. And also, just like the law of reflection, the angles are measured relative to the normal. So the first angle we'll call theta sub 1, relative to the normal in the car, and the second angle, theta sub 2, normal in the car. And again, notice when it went from pavement to mud, that the angle decreased relative to the normal because it bent inwards. And also notice that when it goes from pavement, a less dense material, and mud, a more dense material, the car is going to slow down. So let's take this analogy and apply it to those. The first one, when light goes from a low dense medium to a high dense medium. So for our first scenario, we'll say from a low to a high. So let's draw the barrier between our two surfaces. We'll include our normal. And let's draw our light ray going from the low dense material. And as we saw for the car, when it went from a low to a high, it bent inwards towards the normal. And our angles again are relative to the normal. So we have theta sub 1 and theta sub 2. And we're going from a low to a high. So let's just write down a few things that we know off the bat based on the analogy. The first thing we could say is that when it goes from a low to a high, that its speed decreases. And then we also saw that it bent towards the normal and that the angle decreased. It's towards normal. which results in a decrease in the angle. So the angle decreases. Let's look at a simulation on PhET to see how light behaves when it goes from one medium to the next. Here we have red light going from air into glass. And as we could see, the angle of, when it's from the air, is 30 degrees relative to the normal. And when the light goes into the glass, notice that the angle decreases, it's 19.5 degrees. We can also see that in this scenario, we have partial reflection going on. So part of the light is reflected off of the glass. And based on the law of reflection, theta I equals theta R. And then part of the light goes into the glass and bends, where we can see there's a decrease in the angle relative to the normal. Now notice that when it goes from air to glass, that the red stays the same, the color red, so the color doesn't change when it goes from one medium to the next. So we can also add that the color remains the same. And if we recall from the previous video, color is dependent on frequency, so therefore when it goes from one medium to the next, not only does the color stay the same, but the frequency also stays the same. If we treated light as a wave, we can look at the speed formula for light, which is v equals lambda f, so the wavelength, when light goes from a low density to a high density material. So let's get f by itself since it stays the same. So f is v over lambda. And when it goes from a low to a high, you saw that the speed slows down. The frequency we saw stays the same because the color stays the same. So in order to keep f constant, when the speed decreases, the wavelength also has to decrease, which means the waves are going to get closer together. So the fourth thing we could say is that the wavelength decreases. And again, this is a result of the speed decreasing and the frequency staying the same. We can look at the simulation and look at it as if it were a wave. So we're going to turn this into a wave. And watch the wave fronts as they hit the glass. And afterwards, we can see that they're closer together and that they've also slowed down relative to the incoming light. So because they're slower and the speed is also slower, the frequency will stay the same. So if we were to summarize everything that happens when it goes from a low density to a high density medium or material, we could say, just as a summary, from low to high, the speed, the wavelength, and the angle all decrease, and that the frequency or color stay the same. So let's do the opposite. Let's say now it's going from a high density material to a low density material. That's like going from the mud to the pavement. Notice in this scenario that the right front tire, if it's going backwards, this right front tire is going to, which means it's going to spin faster relative to the tire in mud. And when it spins faster, it's going to bend inwards. But from this perspective, it's bending inwards. And we can see that the angle will increase when we're going from 2 to 1, and also that the speed will increase. So let's apply this to light. So we'll say from a high to a low. So and we're going from a high to a low. So we'll draw a vector to represent our light ray. And we saw when it goes from a high to a low in mud, it's going to bend away from the normal. From the high relative to the normal, and theta 2 and the low relative to the normal. And we're going to say the same thing, but now just the opposite. So when it goes from a high to a low, the speed increases. So think of it going from mud to pavement. It's going to go faster in pavement. We can also say that it bends away from the normal and the angle increases. So it bends away from normal, which means the angle increases. So let's look at a simulation to see what happens to the angle is 30 degrees. This time when it goes into air, it increases 0.5 degrees relative to the normal. Notice that the red goes glass to air. So why don't we put that down? The color and frequency stay the same, since color is dependent on frequency. Oops. Color and frequency stay the same. And again, treat it as a wave. We have v equals lambda f. If we isolate the frequency, that's the velocity over the wavelength. In this case, the speed increases. So in order to keep f constant, the wavelength also has to increase. So the fourth thing we could say is that the wavelength increases. And we can look at it just to double check. We'll treat it as a wave. As it enters the new medium, we can see that the wavefronts get farther apart, which means that the wavelength increases. So if we want to summarize everything for light when it goes from a high density to a low density, we can say from a high to a low, the first thing is that the speed, angle, and wavelength all increase. And just like the previous one, from low to a high, the frequency and color stay the same. Rather than referring to the differences in the materials or mediums as their densities, let's use the physics appropriate word, and that's the index of refraction. And we're going to abbreviate this with lowercase n. And we'll just keep it simple, and we'll say that it's the density of the material. Or medium. And really what it's measuring is how easy is it for light to travel through. The more difficult it is, the slower light will travel. The easier it is, the faster it will travel. The index of refraction is a constant value based on the material, and we could find that inside our Regents reference table. So if we open that up, go to the second page, hopefully. On the bottom of the second page, after the electromagnetic spectrum, we can see that there are indices of refraction. Notice that air is the smallest value at 1.00. Everything else is relative to air. And the highest index of refraction is diamond. We see in parentheses that it's at a frequency of 5.09 times 10 to the 14th hertz. That's assuming that it's white light coming in. So it's the average of all of the visible lights. Let's also define the word refraction while we're at it. And refraction is the bending of light as it enters a new medium and the key word here is that it has to be at an angle. So if we shine lights in a different medium at 90 degrees relative to the normal, so we're going to adjust this laser pointer, and when we shine at 90 degrees, or as close as we can get to it, we see that the light doesn't bend at all. So if it hits it head on, it's not going to bend. It has to be at some angle. Okay, now we can calculate the index of refraction just using the ratio of the speed of light to what the new light is. What the new speed of light is inside that medium. So n, the index of refraction, is c. So we already defined n, so we'll just redefine c as a speed of light vacuum, which is equal to 3.00 times 10 to the 8th meters per second. Decrease relative to a vacuum. So v, in this case, is a speed of light inside that medium, or inside new medium. Notice that the units for the speed of light in a vacuum are meters per second. The units for the speed of light in the new medium are also meters per second. So the units of index of refraction are going to be meters per second over meters per second, is unitless, because the meters per second cancel out. And this is the only other physical quantity in Regents physics that's unitless. The other one was mu, the coefficient of friction. Let's now look what happens when we change the frequency or color of light. We'll put the wavefronts on. And right now we have red light, so we're going to increase the frequency of light. So go to the bar slowly. Watch what happens to the angle of refraction throughout the process. So started at 28.6 degrees down to 28.2 degrees. So when we increase the frequency, or go from red to violet, the angle of refraction decreases, and we can see it's bending more towards the normal. And that makes sense because when we saw white light go through a prism, its frequency bent the most, which was violet. The light with the least frequency, red in this case, bent the least. Also notice that the angle of reflection, 39.5 degrees, stays the same when we change the color from red to violet. Hope you found this video useful. If you did, please like and subscribe. See ya!